All right. So I will get into the topic for today, and this will be the topic for the remainder of the semester. It is going to be various different flavors of artificial neural network. So we'll have 4 lectures on this in total. We'll see how much we get through. I've overhauled this section of the course. Previously, it was rather thin, basically just some very you know I don't know, basic packages in R. Very brief treatment. But here I've tried to make it a bit more robust, develop some understanding of like what these neural network things are. As you know, many people have heard of them. They're quite popular nowadays. But I hope to one, develop intuition is what we're going to do today, behind how they work, roughly speaking. And then maybe a little bit today, but probably mostly on Thursday, we'll talk about how to actually execute these things in R, how to build them, the really nice kind of high level frameworks we have access to in 2022. I like how I had to look at my clock. I'm like, what year is it? So the nice frameworks that we have in 2022, for being able to build these things. It's a lot easier than it was even 2-3 years ago. It's just quite cool. And then we'll see how things go. I'm still building out these notes. They're not done right now. And next week we could probably talk about some of the more esoteric designs, convolutional neural networks, maybe autoencoders, because those are quite cool because they're sort of unsupervised, and whatever else I'm able to fit in. But today we'll start by developing some intuition, and so we'll be talking about concepts here. So basic, not a very deep treatment of this. Really the math on this stuff, as we'll hopefully see, the math is not like some crazy abstract wacky mathematics. It's actually quite simple. It's just that there's so many simple calculations that happen in these things that I would say really the mathematical hurdle that you have to overcome to understand what these things are doing is mostly notational. It's reading the math and getting over how complicated the notation looks, and realizing that it's actually not that crazy. Um, and so we'll talk about this now, just to introduce it. I mean, I'm sure many people have kind of heard about these things already, but they've been very, very popular in recent years. They're used for all kinds of different things, but they've been around conceptually for a while. I mean, I remember reading papers on this, about how they were conceptualized and sort of folks started kind of working with them in the 90s. But really our computational horsepower wasn't really where it is today with that. I mean, like nowadays, if you even want to fit basic models like this, you need to have access to like a GPU, right? If anything real, any real problem, you need to have access to pretty powerful hardware to run these things. And I mean, none of that infrastructure was really around back then, at least publicly. But the idea behind them is they were initially they kind of mimic the way our brains work. And the human brain has roughly 100 billion neurons. I'm not an expert on this. I just Googled it, right? There's 100 billion neurons in your brain. And those 100 billion neurons, there's a ton of connections between them. So each of these, not each of these, but in total in your brain, you have around 100 trillion connections. And what this means is the neurons in your brain, they connect to other neurons. And there's just this enormous network of just stuff that's happening. And the neat thing that in kind of like compiling some of this I don't know, philosophy for this stuff, is that there were some interesting experiments that were done that demonstrated that your brain uses these 100 trillion connections in parallel. And basically the idea, you could simply say, like, you can measure the speed of the electricity, like the signals, how fast they travel from neuron to neuron in your brain. And then you can also kind of study human reaction time, like how quickly a human being can respond to a stimulus. And through those things, you can basically infer that your brain is like this massive parallel computing engine. It must be, if you realize that there's a ball coming at your face and you need to move out of the way really quick, right? It's not going to be one neuron talks to another neuron and then that goes to another one. It's not going to happen sequentially. There's going to be so many different connections that are going to fire in your brain in parallel to tell you, get out of the way. And then you're able to react because of that kind of parallel infrastructure. And really, computationally, that's when these things started to explode. Was when our compute, the way computers started to evolve, really started to, rather than emphasize being able to do one sequential tasks really fast, we started to get multi-core machines. We started to get massively parallel processors that started to sort of, become popular for general purpose computing. In like the early 2000s, those things started to become, much bigger. And so since that has exploded, now suddenly we're able to fit these models really efficiently. It's advancing rapidly in recent years. I mean, you can blink and suddenly everything is different. And so, to put this in perspective with how many connections we have in our brains, state of the art language models are like, I mean, I say language models here because it seems like in my research, these are the guys that are the biggest ones. The biggest models are typically ones that are modeling language because this is a pretty complicated, like our speech is a pretty complicated thing. And just recently, I think it was like a week ago or so, Google AI, they released a paper on this Palm model. You can click this. There's a link in the PDF, of the notes that is embedded in this text right here. That could take you to the archive paper. It's actually quite readable. There's no crazy math there. They just kind of describe what's going on. And like this model here has around 500 billion parameters, and this seems to be like roughly where the ceiling is right now, 500 billion. And a big advancement of this guy is that they're moving past just having a big chunk of hardware on a machine to having a massively distributed network of machines, and they're training these things now on these big data centers that are being used to create these enormous models. And this one in particular, about 500 billion parameters. I'm sure there are more like that are internally in these tech companies. I'm sure they've got giant models. I have friends that work in these places, and they're very tight-lipped about it. But I like to joke that I have a feeling they're there. But anyway, so this is where state of the art is right now, roughly. These very very large models. And I mean, if you think about what a parameter means, this is sort of like like in a linear regression, right? Like one of your betas, that's a parameter, right? And so you may have like 10 of them in your research, right? And just I can't even imagine 500 billion betas in a model. And yeah, so I like to consider, I'm not sure if this is technically correct, but I like to consider the size of these AI models to sort of be analogous to the number of connections, right? So it may be a while before we're really able to mimic the behavior of the human brain. And I mean, that's kind of beyond my knowledge base as well. But you can just put it on the scale. Like we're almost approaching an order of magnitude, kind of nearby, right? And so it's a pretty exciting time. If you have the course text, the Faraway book, I have down here is a little bit trivializing about these neural network models. I don't really know why, but I give the author a pass, I think, as it was, I think the book was published in 2016. So I imagine they were writing it in 2015 or so. And so these things hadn't really exploded at that point quite yet. So, I mean, don't read the book and expect to come away with a modern interpretation of these things. But some of the formulas are there and they look fine. But yeah, so there are different types of models, but they all kind of share sort of a similar structure. The one we're going to talk about this week anyway is going to be the MLP ANN neural network. You can call this multi-layer perceptron, an artificial neural network, just a neural network, a deep learning model. There's a lot of terms that people use sort of synonymously with these. And this one I would call kind of the general purpose model. So the general purpose one being like the other types of models, these are going to kind of use this MLP as kind of a building block. It's going to incorporate, these other ones are going to incorporate aspects of the first in them, but they're going to kind of take things a step further. There are some others such as the CNN, the convolutional neural network. This is really good for finding spatial patterns. So image recognition, for example, like what are the characteristics that make a dog versus a cat in a two-dimensional image? We have various flavors of recurrent neural networks. These are great for when you have like long-term sequential dependencies. So think like time series, for example. And more recently, you have transformer-based models. These are great for like language AI. They're self-learning, they're self-attention, all kinds of neat stuff that's coming out. And it's cool too because a lot of times the theory of these things is pretty much impossibly difficult to keep up with. And so a lot of times you sort of have to follow along just with what folks are doing and how they're applying things to different different types of data. But really the the neat thing about these things is that we have our fundamental building block in the ANN model, and these other guys, and these three. There's many more, of course. Basically, they kind of take advantage of the rather simple construction of the math and how we kind of connect these things together to craft a very specific neural network architecture that will take advantage of a specific data type. So what I mean by that is like, if this is one of the topics I'm including next week, like a convolutional network. Essentially, this uses convolutions, which are special operations that happen to find structure in images, right? And so we're applying a very specific operation to the data to discover patterns that we know are probably there, right? We know, that a dog and a cat, they look kind of different, and you can sort of pick out the spatial features, at least our brains can, that make a dog and a cat, right? Convolutions are specifically crafted to be able to discover those types of patterns in an image, right? And so we include them in a network. Recurrent neural network, same idea. They're built to kind of exploit they're built to exploit like sequential relationships. And so we add very specific math in to these networks to be able to model these types of data. So it's cool the way these things work, and the frameworks that we have available to us nowadays makes it incredibly easy to fit like completely separate models. Like it's very easy to fit these ANN, a CNN, an RNN. It's really easy to fit these things. So easy, in fact, that I'd say it's actually kind of dangerous, like having these easy tools available if you don't know what you're doing. But anyway, it is easy to get going, that's for sure. All right, so to start talking about what they actually are, these, when I say all these parameters and whatnot, essentially what these things go into building is the idea of these, you can call them units. Typically when they're introduced at first, they're called perceptrons or neurons. And these guys are what we use to build, or this idea rather, is what we use to build the entire network, no matter what you're building, right? And so, when we talk about this, essentially what it means is you have inputs coming in, and you typically multiple inputs are going to be flowing in. Then we do some math stuff to compress that down into a single output. And so graphically, that kind of looks like this. And so if you've ever seen a picture of what one of these neural networks looks like, you see there's all kinds of like circles and dots and stuff connecting into other circles with arrows and stuff. But essentially what it means is you have numbers coming in, and they flow into a common pool, and many common pools, and that common pool is that perceptron. And then you do some math and you get a single number for that particular unit. And so like in this example that I have down here, you could say like this, let me change my color here. It's actually rather difficult. So like you could call this, say, X1, you could say this is X2, and you could say this is X3 in the example I have down here. And these guys, they flow in to this perceptron, and then we do some math. Say that math could be this function right here. We are combining all of the inputs. We have inputs X1, X2, X3, and say they take these values 2, -2, and 1. And if we were to crank this through this formula here, we would have 3 times 2 plus, times 2 plus, what do I have? -2, like that. And then -3 times 1, like this. And this is going to give us 1 when we add those together, right? So we've got 6, 4, yeah. And so we end up getting 1 out of that. So basically, this is really the idea of what's happening here is we have values that are present in these cells here, in these neurons, and they flow in, those values flow into the perceptron, they combine together somehow, and they give you an output like that. And that's really the idea. And when we scale these things up, it's just going to be a lot of numbers that are following kind of a similar pattern here with some extensions that I'll talk about in a little bit. So those are really the building blocks of what the neural network actually is, and how we get kind of values into it. And so to express that idea mathematically is, we'll take, say we're talking about a single layer. We have inputs that are going to be the X's, the data itself. Those are going to flow into a neuron, and they are going to have individual weights, Wi. So let's say, like in the previous example, I have some Xi's. So I have, 1, 2, and 3, X1, X2, and X3. Each of those are going to have a specific weight attached to them, right? And that's going to be Wi. So each X, when they flow into a neuron, is going to have a weight associated with it. If I were to go back here, those weights would be, in this particular example that I gave, the weights would be the coefficients that are coming in with the x's, right? So we would have 3 as this weight, we'd have 1 as the second weight, and we'd have -3 as the third weight. All right, so they're coming in like that, and once they arrive, they've arrived being multiplied by their weights. We add a bias term, which I'm going to denote as W0 here, and this bias term is going to allow for the fact that we may have, say, like if I go back to this equation here, to this function, we may have like a +1. You can think of it like an intercept almost, like a +1, or a -3 or something like that. Something that will shift the entire output up or down, and that's possible as well. And so the that shift is not, that's supposed to be a 3, by the way. That shift, if we were to add, say like a -3 to this, wow, 3. If we were to add a -3 to this, this -3 has nothing to do with any of the inputs X, right? But it's still kind of flowing in as well. So we call it a bias because it allows for a shift, and it doesn't, depend on any of the X's. All right, so the Xi's, there's going to be, P of them, as we'll see in my notation, and then they're going to have their own weights, and then we're going to have a bias term, W0, that is going to allow for a general shift. Now, the new piece of technology is the third step. Once they combine together, what they are going to do. So now we have a single value. After we've taken the inputs, we've multiplied by the weights, and we've added the bias. Now, the final step is as they're leaving, or really entering. I mean, really the value of the unit is sort of what's stored inside that cell. But they're going to pass through what's called an activation function, and this is going to be a function that is going to sort of you can think of it conceptually as allowing the value stored in that neuron to fire when it's going to go to a new connection, right? So as that single value that's stored in the neuron is about to go to another neuron, we want to pass it through some filter that is only going to allow it to pass if its value is sufficiently high. Is kind of the idea. And the way this sort of looks like, I think, at least the way I think about this, is that, you have lots of neurons in your brain. They're not always firing. They're not all firing at once, right? Like there's going to be some kind of thresholding that's going to say, you have some stimulus and, like the ball flying at your face, and you got some neurons in your brain that's like, this is my time to shine. I am the get out of the way of things that are flying at you neuron, and I'm going to now fire, right? Because of that specific input that's been passed in and the weights that your brain has learned over your years of having things being thrown at you. And so that's the idea, is that we are going to pass that value that's stored in the neuron through an activation function to see if it will fire, if its value is sufficiently large. Essentially what that means, if it fires, it means that for that input, you're traversing through an area of the network that is capturing a certain feature of the data that is going to, help you predict the final output a little bit better. But anyway, so that's what the activation function's purpose is. But if I combine all this information together, steps 1, 2, and 3, so, inputs, you multiply by the weight, you add a bias, and then you're going to activate at the end. The mathematics for this is going to look like as follows. So we're going to take the weights, and we're going to multiply by the inputs here, and then we're going to add all of these up. Now this, if you think carefully about this, all this is right here is a linear combination, right? And then especially finally, when you add the bias at the end, which is this W0, really, if you think about this, if I were to right next to this write down beta 0 plus beta 1 x1 plus beta 2 x2, say I had 3, plus beta 3 x3, there is not really any difference between what I just wrote right here, this simple linear combination that you probably have seen 100 times at this point in your stat career, and what I just wrote down here. Okay, so this is what this represents. Of course, when I go from the inputs, so however many inputs I have, I'm going to go over those, and I'm going to multiply the input specific weight times the input itself. This part would just be, the part that has to do with the X's right here. And then, of course, the bias, as I said before, is sort of like an intercept, is kind of the idea. And once I do that, I do this process, multiply the inputs by the weights, add the bias. I'm then going to apply the activation function F0 or FO, sorry. And I'm calling it FO because it's kind of like you're going out. You're now leaving the neuron. So the what's being stored in the neuron would be this value right here. And then when you go to leave that to go to the next one, you have to pass through the activation function to see essentially if you're lighting up sufficiently. All right. And when we say what is a neural network, basically it's a scaled up version of this process, right? So you have inputs and then you'll have a bunch of different weights. And then those, you'll have the weights and then those will combine in to make new neurons. And then those neurons, which are the outputs of the previous ones, the inputs, will then go on to be the inputs into a new set of weights or of neurons. And so that's kind of the idea, is we sort of stack these things on top of one another. And I should have a plot. Oh, not quite yet. I have the activation functions yet. And I'll talk about what that means in a second, where we, this kind of stacking process. So as far as activation functions, I've mentioned that their purpose is to kind of like fire for specific inputs, right? If you're capturing a certain feature or something of that data set, various different inputs are going to fire. And that's kind of the idea. There are a lot of these activation functions. The actual form of them, that they, many of them are quite similar. Idea being you want to kind of squish down very small values, and larger values will have a little bit more room to, move around with the input. And so what I mean by that is, let's skip the first one for a second. So like, for example, this rectified linear unit, the ReLU activation, which is probably one of the most popular ones now, is very simple. This activation function says if your X, and again, what this X is going to represent when you're passing it into the function, this is going to be the value of the neuron that's being held in there. When you go to activate that, if that X is negative, you get a 0. And if that X is positive, you just get the value of X. And so we'll see what that looks like in a second. But I mean, basically, it is going to be flat and then it's going to jump up like that. And essentially that means the only way you're contributing to, this activation is if you are positive, right? And everything that's negative is going to get squelched into nothing. And there are others as well. So like the sigmoid, for example, this guy is going to look like kind of that logistic regression that we've talked about here, where it's going to be bounded between 0 and 1 like this. If we had a horizontal axis right here. Hyperbolic tangent has a similar shape as the sigmoid, but it's going to be -1 to +1. So just a different function there. And again, I mean, the purpose of these is to just take an input, which is going to be the value of the neuron. And this can be anything. This can be like, negative infinity to positive infinity. It can be any value that's being stored in there. And it's going to pass through this activation function and it's going to map to something typically smaller. It's going to squish it down there. All right. So in the previous example I gave, in that previous example being this guy here, where I had a few little inputs here, and then I combined them together according to this function, and I got 1 out of this as the output. If I were to then activate that with the activation functions I just showed, with the identity, which by the way, to step back to that, the identity activation function is not really an activation function. It just passes it through, right? So whatever you put into this function here, you're just going to get that out. And this is necessary for like output layers when we want to, as we'll see, when we don't want to change anything, right? Like whatever value flows into that neuron, we want to keep it. And this is typically the case, when you have a final Y that you're predicting, is when you want to use this guy here. Okay, it's also called linear, the linear activation function. It's not doing anything, basically. It's allowing you to output exactly what came in and was stored there. Okay, but anyway, so if we were to take that 1 that we had and we were to, pass it through these different activation functions, obviously with the identity, we're going to get 1. With the ReLU, we would just check the logic here and see, all right, well, 1 is greater than 0. Therefore, 1 is the value that we're going to get out of this. So that's good. With the sigmoid and the hyperbolic tangent, slightly more complicated. All we got to do is just plug our 1 in for X in these functions here. And you're going to get these values respectively for that value of 1 on that. So it's just passing in the X and getting the value of Y out of it. So this is what they look like, in case it's not clear. So the identity, so we have, just to draw some dashes here, we have our 0 and 0 here. You can see the identity function is basically not doing anything, right? Whatever you put in, you're going to get that out. The ReLU, however, you can see this guy has kind of the elbow at 0. After 0, After x equals 0, suddenly this guy kind of spikes up. And in fact, at this point, given that the x that you put into the ReLU is positive, you're going to get out whatever you put in. So this is this activation function. Basically, if your value that you have stored in the neuron is not doing anything, it's just going to get pushed to 0. Nothing will happen there. Sigmoid, you can kind of see the S shape a little bit. I took care to put these guys on the same scale here. And so the sigmoid, there is an S shape here, but it's a little bit flatter. But the hyperbolic tan, you can really see the S shape here, but it's more stretched out, right? So this one goes from -1 to 1, and this one goes from 0 to 1. The sigmoid does, and then tan H goes from -1 to +1. So these are just different activation functions, and we'll see where we're able to kind of plug these in. But really, as far as like mechanistically, the purpose of these, as I said, is to take any input that you could technically have in that neuron, and when you go to use that, it's going to pass through this activation function to say, is this output something that I want to consider, more or less, is the idea. Okay. So, to kind of summarize what's happening here, the initial thing that I'd showed you, the first like perceptron graph here, we just had simply some inputs, and then they go into a perceptron, and then you go, you get the output here. And this right here is basically where that activation function would apply. So when you're about to leave and go to a new neuron, you would apply that activation function at that point. And so really this perceptron thing is very general, and it doesn't, these inputs that I have in green right here, these don't necessarily have to be X's. These guys could be the neurons that already exist in the network. So these guys have already active. Maybe you have like, you've got 1, 2, 3, 4, 5. Maybe you've got 5 X's. So this is X1, X2, and you get the idea up through X5 here. And maybe these guys, maybe this is connecting to each of these X's is connecting to these like that. Oops, sorry. Going up here. So basically it would take me forever to draw this, but the idea is each of these X's here could be the real like inputs, like the X inputs. So the XIs, this is like the data. They are going to flow into this first perceptron up here. And then they're also going to flow in, as I started to indicate, they're going to flow into the second one as well, along with X4 and X5. They're going to flow into the second neuron. And then they're also, all 5 of these, going to flow into the third one as well. Okay. Now, in that case, we now have 3 values. We have H1, H2, and H3 is typically how they're notated. And so what these guys are representing, these are the, after you've passed in those inputs, you have stored a value in each of these neurons that represent separate weighted combinations of the inputs that I've just drawn on the left here. Now, it could be possible that these hidden units that are now, they were the outputs of the previous inputs, now become inputs to another output here. And so more or less what we're doing with these is we just treat, the perceptron idea where you have inputs coming in and then you do that math with the activation function to get that output. And we sort of just connect a whole bunch of things together. And once you do that, you end up getting something that kind of looks like this. And it's drawn slightly better than I had. So the inputs, the XIs here, these are like our covariates, right? So the X data that you have in your data set is represented by these P neurons right here that are coming in, right? So this is just the data. These are just, these are fixed values that I have in this curly bracket on the left. Each one of these guys is going to connect, if you look carefully, is going to connect to every single one of these hidden units, of which I have capital J. Right? So I have capital J of these hidden units, and you can see first, kind of both things are true. The each of these X variables are connected to every single one of these nodes, and each one of these guys has a connection coming from every single one of the X's, right? So it's a completely fully connected network here, right? So those are the XIs or the covariates, and I'm using the H subscript J notation. These are the individual perceptrons that we have, the nodes themselves. I'll call them units typically. Neurons is another thing that people say. But again, the important thing is each one of them is receiving a weighted input from every single xi, as well as a bias, by the way. The bias here is not pictured. So also you have a separate bias here that is separately. You have a bias for this neuron. You have another bias for this neuron and for this one, etc. So this guy is kind of separate because it's not depending on the input, but you still have a bias, for every single one of these units as well. All right. And so each one of these guys, if I can erase, each one of these guys is going to have a weight. So like when you go from X1 to H1, you're going to have a weight for X1, and then that's going to H1. All right. You're going to have a weight from X2. I forgot what my notation is here. Stand by. I want to be consistent. And then I'll come back. Okay. Yeah. I have the variable second. I just want to stay consistent with what I have coming up. So you also would have the weight that's going to the first hidden unit for the second X variable. And then here, this guy right here, going from X3 to H1, this guy would be right here. This line would be, you'd have the weight for the first hidden unit, the third, from the third X variable to the first hidden unit. And so each of these guys, each of these X's is going to have their own unique weight when they combine together to, multiplying these to these guys and then adding up and giving you this, this hidden unit. And you'd also, of course, have a weight 0 for this guy as well. And so for the bias as well. So each of these connections is going to have their own unique weight, which means the number of parameters you have is going to grow, as a multiplication of how many X's you have and also how many hidden units you have as well. All right. So each of those hidden units or hidden neurons is going to have a weight from each X as well as a bias. All right. Then once we have this, and I'm going to talk about the, the simple case right here where we have inputs, we have one hidden layer in the middle here. Really, so, for the first example I'm going to be working with when I explain the notation, really, I mean hidden layer. So right now we're just going to have one. Later on, we'll see when there's more than one. All right, so we have inputs, we have hidden layers, and then we have outputs. This can be plural. So the outputs here, these guys are also, let's focus on the first one for a second. These outputs, this is going to be the Y, like the response variable that you're trying to predict. All right, these guys are also going to have their own weights that are coming from the hidden layers and going to each of the neurons in that output layer. And so, now this is really where the thing that I had said before kind of comes back, which is that the perceptron idea deals with, you have inputs going into the neuron and then you go out, right? And those outputs could be going to another neuron, which is considering, the first one I mentioned, the input, right? So you have inputs that, they combine together into a neuron, and then that neuron can become the input to a subsequent layer later on, right? So here, as I mentioned, we have H1, which is the combination of all of these X's, right, plus the bias. Now we have this one neuron is then connecting to Y1 along with all of the other hidden neurons as well, which themselves were combinations of all of the X's and their own unique weights. So you can see the number of connections that we have here, while individually they're pretty simple, right? It's just you have some weights and you multiply by the X's, and then you add a bias, and then you apply a simple activation function to get each of the numbers that are in here. Once you kind of, trace out how you finally get one of these Y's, there are a whole lot of little tiny calculations that are happening to go from one of these, a set of these to a set of outputs, right? So input to output, there are a lot of little connections that have to happen. Okay, so again, these guys here, each of these, they have their own weights coming from each of the individual hidden units. And I believe the notation I use here is beta. They're going to have their own beta parameters that are going to be, you have one for this connection right here. We'd have a separate beta connection for this one. Again, these are all the ones that are flowing into the outputs Y for this. Now, just like lowercase p here is the value that tells you how many X variables you have. Capital K is going to be the number of outputs that you have. And so say you have a regression, like a simple, you have a set of X variables and you have a single Y variable and you're trying to predict In that case, the capital K would just be 1 because you just have one output. It's a single number. The cases where you have multiple outputs, typically, not necessarily always, but typically are going to be like for classification problems. Like if you have a 10 class problem, you have 10 categories. You're trying to predict which one of 10 categories an input is, then your K would be 10 in that case, because you're going to have a probability of being class 1, probability of class 2, class 3, and so on and so forth. Okay, and so that is what those guys mean. So the K, capital K, is the number of outputs that you have. For regression, often this is just a single number. It doesn't have to be. It can be 2 numbers as well. But for classification, it's definitely going to be more than 1 because you're going to have an output for every single class probability that you would have. So to start to combine some of this together, some of the math that we've already talked about, and say how do we essentially go from inputs X to the final Y output. Basically, we could say if we wanted to have the individual value for an HJ, really the output of one of the hidden units. So this is so this J here, by the way, for a particular layer. So the hidden layer that we have in the middle there, this J index is going to go from 1 to up to capital J. And this capital J here is going to represent the number of hidden units you have in the middle here. So you can see here, capital J is the bottom, on the bottom of that. So each of these individual HJ, each of the neurons, they receive an input from every single variable, which is going to have a weight that is going to be notated as WJ comma I in the subscript here. So J here is going to be the neuron that it's going to, and the I is going to represent the variable it came from. Okay, because remember, when we look at this picture over here, each of these neurons in the middle, they have a connection from each one of the X's. Okay, so to get to H1, you have to have the weight coming from X1, the weight coming from X2, the weight coming from X3. And so what this notation, means is basically to say I want the weight for HJ. So of like H1, for example, I want the weight for, or excuse me, the value for that first neuron. I'm going to have W1 comma 1. So that's the weight for H1 that's coming from X1. I'm going to have the weight for neuron 1 coming from X2. That's going to be W1 2, and so on and so forth up to W1P for the first hidden neuron there. All right, so every hidden unit is going to have its own unique weighted inputs. Soon as I go to the second one, when I go to H2, suddenly that connection from X1 is completely different now, right? So like you could have one coefficient that goes from X1 to H1 and a completely separate one that goes from that same X variable to H2. Completely separate coefficients that go, to each of these individual neurons. And so you're going to have, that number of parameters basically. So that is going to give us each of those weights. So if I want the value for that neuron, the jth neuron, I'm going to have to make sure that I respect the fact that each of those X's is providing a unique weight. And then I have an HJ specific bias, which I will denote as WJ comma 0. Right? So the 0 because it's not with any of the X's, because we start the X's with 1. All right. And then after that, we combine these with a linear combination. This is just the general structure of these things. And then you activate it at the end with the function f, which is the activation function. And so this is basically the same as what we looked at a few minutes ago. But, just to be a little bit more specific here about how the inputs work, in that I'm going to have the sum from I equals 1 to P. And so this is going over my X variables now. So the I subscript here is representing an index for the variable. And then remember, I'm considering a specific neuron right here. This is going to be, I'm going to add up, the products, the weight for that particular neuron for that particular variable. So WJI multiplied by the input itself. Okay, so linear combination of those input specific weights times the X's, and then I add the bias at the end. and then I activate it, and now I have the neuron or the outputted neuron or whatever. So after I've activated that. Okay, so I do that for every single neuron. I do it for H1, I do it for H2, I do that for H3 up to HJ. And now I have essentially numbers that would be coming out of each of these. Let me erase. I now have numbers that are coming out of each of these hidden units in the middle here. Okay, and those numbers now, they sort of you could almost think of them as variables themselves, right? So in the beginning, the first step that I just talked about, we had our px variables, and they went into all these neurons with that, the neuron specific weighted combinations to go into these. Now we can almost think of these guys as an abstracted set of variables that will then flow into the next and final layer, which is y. And so we end up having a very similar aggregation here, which is that the y, instead of like the h's were receiving input from every input variable x, and then we combine them together with this expression here. Similar to that, the y's are receiving input from each of the hidden units, j. So the x's are feeding the hidden units, and then the hidden units are feeding the final y values that are coming out. And so these guys are going to have their own weights again. And so these guys are going to be weighted by beta kj. So the beta here, this is going to be analogous to the w, the weight. But these weights now are going to go from the hidden units themselves to the outputs y. And so the notation there to stay consistent with this is that we're going to output k, little k, and we are coming from hidden unit j. All right, so the subscripts are a little bit different here because we're talking about where we're going to and where we're coming from. And so there's going to be a weight, again, separate for each of the output units, meaning, however many output classes or variables we have. For each one of those, we're going to have a unique weight coming from each of the hidden units. All right. And also we're going to have a specific bias or a YK specific bias, meaning each of the outputs is going to have their own bias. And so to draw this here, we have to talk about where we are going to, again, where we're going to and where we're coming from. And so basically what that's going to mean is that the weight going from H1 to Y1 here, this is going to be beta 1 comma 1. This guy right here, that's going from H2 to Y1. This is going to be beta 1 comma 2, and so on and so forth. So now we're going to have a whole bunch of betas here. Each of these lines that are crisscrossing, going from the hidden layers to the output layer, these are each going to be a specific weight that tells you how to combine the hidden layer, the values that are coming out of these hidden units, how they go and aggregate together to give you the final output values there. And again, we also have a bias that is going to be unique to each of the Ys. So you'd have a bias for this and a bias for this guy, different numbers. These lines here, just like all the rest of these lines, these are going to represent different numbers that can represent the shift in this. Okay. And so with all that said, I just want to point out that the way we get the hidden units, which was to take the weights that tell you how to go from the X's to the, those hidden, each of those capital J hidden units, that function where we had the linear combination and then we added the bias, you can see, like, if you look carefully, and you don't even have to look that carefully, the form of these guys are pretty much identical, right? Like, we're just taking now, instead of X, the X's were the inputs to the HJs, we now have the HJs as inputs for the Ys. And so instead of having the W's, which were the weights to go from the inputs to the hidden layer, we now have the betas, which are the weights that go from the hidden layer to the output. And then we also have the biases that give us those general shifts that we may need to get to the output. Again, output specific. Okay, so that's the idea. All right, so if that all sounds a bit confusing, I don't blame you because it is tricky to understand. Like what does it mean when we have these units and they combine together, especially when we talk about activations, and how that works to model these really complicated relationships. Because really the place, I didn't really mention it in the beginning, but the topic of this, technically, the topic for this topic is modeling nonlinear processes basically with these neural networks is the idea. And so, how did these things combine together to model complicated nonlinear relationships? And if you think about just for a moment the ReLU function like this is a very simple thing. It's essentially just like a straight line. How do these straight lines capture nonlinearities? And if you think about it, what I'm going to demonstrate here in a little bit is essentially the idea is like if you had some kind of like parabola like this is not a straight line, right? But if I wanted to capture this thing with a few straight lines, what would I do? Let me change the color, make it a little bit more obvious here. If I wanted to capture this with a few straight lines, I could do, all right, maybe a line here, maybe I'll have a line here, and then I'll have a line here. You could very strategically create three straight lines that would be able to pretty well capture this, parabolic pattern here. And that's kind of the idea with, looking at how these activations can capture nonlinearities is it's not in the activation itself, it's in how you combine them together. So let me show you what I mean by that with several slides. So the first thing that I'm going to do, now we're kind of going into code land to explore this activation idea. I'm going to create a my ReLU function here. What this is going to do, this is going to take an input X, and I'm passing it then through through an if else, which is going to vectorize some logic. So basically, knowing that the function I'm trying to capture, let me switch my color back here. The function that I'm trying to put into code here is f of x is equal to, and I've got 0 or 1. This is if x is less than 0, and it's 1 if x is greater than or equal to 0 here. And so this is what I'm doing here, allowing it to pass in a vectorized x. If x is greater than 0, I'm going to give back x. Otherwise, I will give back 0. Okay, so that's the idea. Then I'm going to create a sequence of x's here. We're going to go from -2 to 2 and, reasonably granular view into that. And the first thing that we're going to do is basically identical to what we looked at before, is to say, what if I have a single hidden unit, h1, and this is just going to be, the weight for that guy getting into it is 2, and then I have no bias. The bias is 0, and the input is x, right? And then there's no overall bias to get to the final y. What this would look like is I would have the x here, and then I would have the output y, and that, this is what the relationship would look like, because I have a single value right here. I'm passing in an x, and you can see if I have anything greater than 0, I'm just going to get 2x out of that. And you can see, if I had 1, I'm going to get 2, right? So to kind of take a step past what I was just saying and looking at the, that parabola sort of relationship there, if I were to take 2 of these ReLU activations, so 2 hidden units, say my first one, I have a weight of 2 right here, and then I have the x and no bias on this. And then for the second hidden unit coming from the input x, I have a weight of -3 and I have a bias of -4. So if I were to take this and apply this in, you can see what's going to happen is if I look at this plot on the right, starting from 0, it looks identical to what I had before, right? So it's still, I got this increasing relationship. That's essentially y equals 2x. And so, but what's happening before that is interesting now, because now I'm incorporating this part as well, which is to say that I have, the -3x -4. If I were to put in, say, -2 into this, putting -2 in to this part, I'll start with h1. So say I have an x which is -2. If I look at this first term, the h1, this is going to flow in. I got -2 times 2. That's going to be a -4 living in this first neuron. And then when you activate that, I'm going to get 0 because it was -4, and that's less than 0. Therefore, nothing will happen with this hidden unit. It will not activate coming out. However, in the second hidden unit, what's going to happen there? I've got my -2. That's going to come in. I'm going to multiply it by -3. So I'm going to have a +6. And then -4 on the bias. This is going to give me 2. Now I activate this. And then I activate the 2 with a ReLU. I'm just going to get 2. That's why I'm here. Okay? So really, those steps where you have the input and you multiply the weight and you incorporate the bias and then you activate it, this is what you end up getting out of that. So, and you can see similarly, if I were to put in, 1.5, I'm going to get something right around here. And then, in this middle part, you can see I'm at 0 because, I mean, you can look and say, all right, I got -1 coming in, -1 times 2, -2. This guy's going to, push to 0 when it activates. Same deal here. -1 times -3, that's going to give me a +3, -4, -1. So activate, it's 0. So I have 0 plus 0. Gives me this final value. And so basically the idea is I have these two linear functions in here, right? So these are essentially like the W0, I'm going to abuse notation for a second, plus the sum of I equals, 1 to P, which is just 1 here, really. So actually, I don't even need this. The bias plus the weight 1 times the X in input, right? So I have two weights that are associated with this. I pass them in from the X, and then I activate them, and this is what I get. And so taking this function, knowing that, H2 had these, weights and biases, H1 had its own weight and bias. By combining them together, it ends up looking like this. If I were to kind of draw this out, I guess I could do that, given that I have the space here, I have 1x, right? So this is x. I'm going to say x1, just to stay consistent with previous notation, and that's representing this x right here. I have two hidden units. I have here h1, and I have h2. When I am going to h1 from x1, my weight for this is going to be 2. So I'm going to have a 2 right here. When I go from x1 to h2, my weight is going to be -3, is going to be the weight. And then if I have a bias up here, the bias going to h1 is going to be 0. And the bias going to h2 is going to be -4. Like that. Okay. So that's the idea. And then once I come out of this, once I come out of these guys, now I'm going to be passing it through the activation function. And so, that. And so these guys, when they combine together, I guess I should be a little bit more. Ooh, where's my eraser? What? Oh, sorry. I got to erase over here. Stand by. So then when these guys go to combine together, these hidden units will combine together. This is going to go, H1 is going to come in, and these guys are going to go to create Y right here. And then this, so we look at these individual weights. When we're determining Y now, the weights that are here are going to be 1 and 1, because we are simply, after we activate those hidden units, we have 1 times H1 and we have 1 times H2, because we're just adding here. So these guys will be 1 individually. And then the bias to go from the hidden layer to the Y, this guy is going to be 0 here, because we have no intercept when we determine this final Y. That's the idea. All right. Good. So with that, I want to kind of take it up one notch slightly and say, what if we were trying to approximate an actual like nonlinear function? What would we do? So I sort of just cheated, and not cheated, but I hard coded some weights and biases. I basically explored using way too much time to try to figure out something like this, like a combination of very specific weights and biases that are going to give me a set of lines that are going to reasonably approximate this sine curve. All right. So I'm going to say x is going to go from 0 to 2 pi. So I'm just going to do one cycle of the sine wave. I'm going to create the sine x by passing that x into the sine function. And here we go. I just have a plot right here. So what I want to do here is I want to find some hard-coded weights and biases that give me straight line approximations that approximate this function. What's that going to look like? We start off first, up here, I have the code is identical, like up to this point. All we've done is generate the X's, the Y, do a plot. So the first thing I'm going to do is I'm going to say, all right, what if I have one unit that I'm sort of crafting directly, which is going to just be 0.7 times X. So I input some X from this, and I'm just going to multiply it by 0.7. And once I do that, I'm going to pass it through the activation function. And then that is going to be, what I will contribute to the Y on that. So notice I have, I've kind of already noted this in the comments here. But the 0, this is going to be, when I go to determine the final Y value, this is going to be that output specific bias here. And then, the 1 times H1 here, this is going to be the weight going from the hidden layer into the final value. Now, if I want to know those same aggregations coming from the input into the hidden layer, that's what these are, right? So first things first, I have the 0.7 times X. So, basically you can kind of see it's going off the page here, but, anything I plug in that's greater than 0, anything I plug into X, I'm going to get a positive value. So I'm going to end up just getting, 0.7 times whatever X is for that. And so therefore, if I just have this guy after activation, I'm just going to have a straight line, and this guy is actually going to go up forever, right? It's just going to keep on going. So it's going to go forever up in that direction, but I don't want that, right? Certainly up to here, at least for something that I'm crafting myself, this is reasonable, right? Like it's somewhat mimicking the pattern up to this point, but I would kind of like it to take a turn and then go down that way. So to do that, we will add in a second hidden unit that I, again, am crafting. So in this case, the weight going from the hidden layer into Y is going to be -1 because I want this guy to go down in this case. And then the coming from the X getting to the hidden layer, I have a weight from that 1X of 1.5. And then I have the bias being -2.5 there. And so this is basically telling me the shape of this this line, right? I have sort of a slope. And again, remember, it's combining with this one to, given that they've both activated, it's combining with this one to determine the final value of this line right here. All right. And then I could do this one more time, add a third layer, which is going to give me a final turn down here. And this guy, my output specific bias is going to be 1. And then my input to hidden layer bias is going to be 1.5, or excuse me, weight is going to be 1.5, and the bias would be -7. So if I were to kind of draw this out, I guess if we were to look at this just like we looked at the other one, we would have one input, we have one output, right? We have a single X coming in, we have a single Y coming out, and then we have 3 hidden units. So I think what I could probably do is kind of sketch this in here. So I've got my single X right here, and then I have 3 hidden units. So we got 1, 2, and 3. We're going to have a bias coming from up here, and then we're going to have a single output Y right here. Let me just give myself a tiny bit more room on this guy. Okay, so this is the X. This is the Y. Here we have H1, we have H2, and we have H3. All right, so to get from X to H1, like this, the weight that we're going to use to get from H2 to X1, that's going to be this guy. This is going to be 0.7, like that. And then the bias for that is going to be 0. All right, to get from X to H2, you can see my weight is 1.5 here. All right, and then finally, to get to H3, again, I have a weight of 1.5. On that, forgot the bias. So the bias going from that helps us get to H2. This guy is going to be -2.5, and then the bias that takes us to H3, you can see how messy these get, is -7. And then now, once I activate, I'm coming out of these, and now I'm heading to Y from each of these hidden units like this. And then I'm going to put a bias up here. And so the once I have the hidden units, that represents, say, H1, coming out of H1 is what I'm putting in brackets right here. It's this entire piece right here. So it's like, what do I do to this now to aggregate it to the final Y? So from H1, my weight is going to be 1. For H2, my weight is going to be -1. And for H3, my weight is going to be 1 here. So you can see like what's happening there. And then finally, my bias here is going to be 0. Because I didn't have any like global intercept to take me to that point. All right, so that's kind of what that would look like. Probably you'd have to watch the video to see how those chicken scratches come to be, because I look at it now, I don't know what I'm looking at. But yeah, so that's that. That's how that sort of how they aggregate together. So when I take all of that, I'm gonna do one simplification of notation here. The bias can be kind of this sort of one-off that makes the notation a little bit complicated. So just looking at like what I have right here to the left of this, the where I had the bias plus the linear combination of the weights and inputs, I'm basically just going to say that x0 is equal to 1 and h0 is equal to 1. These guys are not part of, if you were to look at the, if I find the neural network diagram here, I started at h1 and up to hj. Same with x's. I started at x1 and went up to xp. This guy is going to be, I'm just going to define x0 and h0 to be 1. That way, when I want to incorporate the bias, I can just kind of wrap everything into one sum and say, instead of going from I equals 1 to p, I'm going to go from I equals 0 to p. And so knowing that the first guy, the x0, is just 1, and therefore the weight that I have is just going to be this guy, right? Because I would have wj 0. So it's the bias. It just allows me to bring that term into the sum, just to make the notation a little bit nicer. And I'm doing that with both the hidden unit and the x's, so that, also when I go from hidden layer to y, it's the same deal. I had the bias, the output specific bias, and then I had the linear combination of betas and hidden units. There's a typo here. This should be hj. There should be an hj factor right here. So that's missing. So I will correct that. If you've printed the notes out, I apologize. So just note that for now. Okay, and so this guy, once we simplify that notation, it will be sum from j equals 0 to capital J instead. Of course, having the hj here, as it should be as well. Okay, and so once I simplify that notation, the reason I want to do that is basically say, once I have all of these weights, like once I have the weights and I have the, that go from inputs to hidden layer and hidden layer to output, once I have those W's and the betas, I can do this function that I'm looking at here to go from an arbitrary set of inputs X to, the Y's that I would predict for it. Once I know what these weights are, or I have a good idea of what the weights are, I can pass in an X, and then I can crunch it through all this math where I'm taking the weights that I have to go from input to hidden layer. And then now I activate that. And now suddenly this guy here, this guy now becomes hj, like that, what I have with curly brackets here. And then, that's going to be used to go from the hidden layer. And then you multiply by the weights that are associated with those hidden layers to go to the output, and then activate a final time to get the actual y that is at the end there. All right. So that's the idea. That's how you go from total input to what the output is. And yeah, so what I want to point out here is that the number of weights here are actually quite large. So to get from the inputs to the hidden layer, there are j times p plus 1 weights, right? So for each of the x's, there's going to be p of those, and then add the bias, that's one more, right? And so each of that collection, the bias part, and then every single one of the x's is going to go to each of the capital J neurons. And so therefore, you're going to have p plus 1, and so p plus 1 weights for every of the hidden units, and then times j of them. So you're going to have j times p plus 1 weights to go from input to hidden layer. And then similarly, to go from hidden layer to output, you're going to have capital K times j plus 1 weights there. So there can be quite a few of them. I mean, if you think about, I've got 3 X's and, 1 Y, and then you have a decently thick middle section there, there's going to be a lot of parameters that end up making that up. So I'll just, whet your appetite for what we talk about on Thursday before I start diving into this. The number of parameters can be quite large, and we have to think about how we're going to learn them. I mean, there's not going to be like a nice formula that's going to say, okay, give me your X's and Y's. Let's do this simple formula. And now, boom, we have the weights. That's not possible. What we're going to do or talk about is something called backpropagation. And this is basically using a calculus concept to, say, we'll pass the data in, and then we'll get a prediction out. And based on how good of a job we do with that prediction, we'll then adjust the weights to try to make it a little bit better. And then we'll just keep on doing that a whole bunch of times. And then eventually we'll find some parameters that are good enough, typically. Never perfect. It can never be perfect or, ideal. At least it's not generally the case, but that'll be generally how we do things will be with this algorithm. And I will talk about that on Thursday before we talk about how to actually fit these things in R. So yeah, so that will be it for today. I appreciate everybody coming by. So thank you, and I'll see you Thursday.